So let's imagine that you have already identified that you have two different samples, and those observations within those samples are independent of each other. Okay, so we're headed to the independent t-test, and just like all of our inferential tests, this independent t-test has a specific formula associated with it that we can use to quantify that difference between the means of those two samples. So don't be overwhelmed by the formula. It may look like a lot going on in here, but really there's only 6 pieces of information that we need to calculate this. We need to know the mean of each of our groups, we need to know the sample size for each of our groups, and we need to know the variance for each of our groups. So really, other than that, it's just simple algebra. Notice what the numerator is doing here. It's literally just taking the difference between the means. So hopefully this exemplifies how, even though every test has its own formula, that formula has been very carefully designed to quantify exactly what it is you're testing. And for us, we're testing for the difference between two sample means. So that's why we're initially, for this numerator, just taking the straight difference between those two sample means. But we also know that inferential tests have to account for how much variability there is in those groups, and also has to account for the sample size of each of those groups, because that's how power is incorporated into the test. And so notice down here in the denominator, that's where we get into all the variability for the two different groups and the sample sizes for the two different groups. There can be an issue with the order of operations. So notice how many parentheses within brackets, within other functions there are. So if you were doing this by hand, you would have to be very careful. So luckily, you will hopefully never have to do this out by hand. So if I'm not expecting you to do this out by hand, why am I showing it to you? And it's because we can't just think of all of these different software packages as black boxes. We have to understand what they're actually calculating and how they're calculating it. You should be able to see this and recognize it and know what it's doing. And by seeing what it's doing, you therefore can know which test this is associated with. So let's keep going in that vein, though, so that we understand the foundational basis for how this t-test is run. If you were doing this by hand, you would calculate this formula, and this is your obtained value for your t-test, or your test statistic, sometimes called your calculated value, your test statistic, or your obtained value. That just quantifies the difference based on the amount of variability and power of the test. It doesn't tell us whether or not we have a significant difference. For that, we have to compare it to a critical value. Okay, and so for that critical value, we need a little bit more information than we did when we were doing the one sample z-test. Right? When we were doing that one sample z-test, all we had to do was look up that z-test statistic, the obtained value, and we could see on a normal distribution what the probability was associated with that. But to get the critical value for a t-test, we need to also know whether or not we're doing a one or two-tailed test, right? Because these are actually going to be in different tables. It's not as easy as it was in the z-test where we could just double it for a two-tailed test. So we have to be using two different tables depending on whether it's a one or a two-tailed test. Obviously, we have to know the significance level for our test because that's going to tell us where that critical value falls. But we also need to know the degrees of freedom that we have for this test based on our sample size. This is the first time we've ever mentioned degrees of freedom, so I don't blame you if you're saying, what the heck is that, Jen? So let's back up and talk about degrees of freedom for a second. Degrees of freedom is something we have to know for each of the different tests that we run. As you get into more complex formulas for your different tests, the degrees of freedom are a way to approximate your sample size while accounting for how complex the formula is. Right? The more complex the formula, the more you're going to need observations to be able to really approximate each of those parameters that go into the formula well. So the official definition is that degrees of freedom really represent the number of values or terms in that final calculation of your test statistic that are free to vary, right? So it's totally dependent upon your sample size. Whenever you figure out degrees of freedom, sample size is going to be a component of that. But how you actually then figure out the exact degrees of freedom is going to vary depending on your test or how complex that formula is. Lucky for us, it's pretty straightforward. We just take the number of observations in our first sample, add the number of observations in our second sample, and then subtract 2. Essentially, we're subtracting 2 because there are two main terms in this formula, the mean, calculating the mean for the first sample and calculating the mean for the second sample. Okay, so again, to summarize the information we need to know to find the critical value for that independent t-test, we need to know whether or not we're doing a one or a two-tailed test so we can get to the right table. We need to know what our alpha level is, what our significance threshold is, because that's going to bring us to the right column in that table. And then we need to know how many degrees of freedom we have. That's going to bring us to the correct row in our table. Okay, so let's take a look at what this table looks like. Here is an example of the one-tailed, or they call it the one-direction t-table. Okay, so notice that our columns, they give us some of the standard or most common alpha levels. We have this 000 really stands for less than 0.001. Here we have 0.005, 0.01, 0.025, 0.05. This would be the standard that we typically use, and then 0.1 for people who think they have very low power for a test. So that's going to tell us which of these columns to go to. But then we need to go to the correct row based on the number of degrees of freedom that we have. Now notice as your degrees of freedom gets larger, there's jumps in between each of these different rows. It goes from 29 to 30, but then from 30 to 40, and then 40 to 60, 60 to 120, and then to infinity. And the point is that the higher your sample size, as you get larger and larger, the less of a difference one or two more observations makes. And it gets to the point where even large jumps in the number of observations doesn't make that much of a difference. So for example, jumping from 60 to 120 degrees of freedom at the 0.05 level really only changes your critical value by 0.2. So it's kind of negligible. So that's why these tables are made at this sort of coarse level. What do you do if your degrees of freedom doesn't show up on this table? Just go with whichever is closest. Then once you know which column and which row you need to be in, that's where you're going to find your critical value. This is the value you have to beat. If what you calculate is not more extreme than whatever your critical value is, then you do not have a significant result. There is no significant difference between the groups. But if what you calculate is more extreme than this critical value, then you know you have a significant result. Just one thing to be aware of, those t-tables do come in different flavors. Usually you'll see a different table or a separate table for the one and the two-tailed test, but there are some tables where they just lump them together. And they can do that because, as we learned with the one-sample z-test, those probabilities associated with the two-tailed test are really just double the probability of the one-tailed test, because that normal distribution is a mirror image of itself on either side of 0. So you can find some tables where they will just lump these right on top of each other. The two-tailed test is just double the probability of the one-tailed test, right? So the critical value for the 0.05 one-tailed test for given degrees of freedom is going to be the same as the two-tailed test for 0.1 instead of 0.05, so double that probability. If you weren't satisfied with just saying, yes, this is significant, you could use the Excel function to return the probability associated with that given calculated test statistic. So just like we did with the z-test, where we had the norm Ttest to give us a probability associated with a given z-score, we can use a Ttest function to look up the probability associated with a given t-test statistic. But because what the values are for that t-test probability depend on whether it's a two-tailed or one-tailed test. And also Excel recognizes that we might want to differentiate less than, which would be your left-tailed test, from greater than, which would be your right-tailed test. They give us 3 different functions. If we want to just do a two-tailed test, we would just enter t.dist.2t, and then we would enter that calculated t-test statistic that we got from the formula, and we would enter our degrees of freedom associated with that test, and it would give us the probability for a two-tailed test. If we were doing a left-tailed test, so we wanted to know the probability of being less than a calculated test statistic, we would just enter t.dist, again, enter that t obtained value, enter the degrees of freedom, and then give it this little 1 at the bottom to specify that left-tailed test again. If we wanted the right-tailed test, we just need to enter t.dist.rt for right tail, again, give it that calculated test statistic for the t-test and the degrees of freedom. But Excel also has other functions associated with the t-test. If you have all of your observation data included in a spreadsheet already, you don't have to go through calculating the formula. You can just actually ask Excel to give you the results of a t-test, and we just use the t.test function. Okay, and what this is doing is it's basically bypassing us having to calculate that formula for the test statistic. All we have to do is go in and highlight which array is our first group, put in a comma, highlight the array for the second group, put in a comma, tell it whether we're doing 1 or 2 tails, put in another comma, and then put in either a 1, 2, or 3 to specify which type of t-test we want. And for this independent t-test, you want to select a 2. That gives us a 2-sample equal variance t-test. And that was one of our assumptions for this formula, right, was that we assumed equal variance. So if we select this 2 for this last input of the function, it's going to give us the same result that we would have gotten if we were calculating it out by hand. Okay, so the syntax for that, you would just say equals t.test, put in your parentheses, highlight array 1, comma, highlight array 2, comma, enter whether it's 1 or 2 tails, comma, and then enter the number 2 to specify that you wanted a 2-sample t-test assuming equal variance. Okay, here's an example of what this looks like, right? Imagine that I have these observations and I have recorded the value for each of these. For these 20 random observations, I went back and took 20 other random observations for a different grouping. This was unremediated sites, this was remediated sites, and I can just highlight those 2 arrays in this formula. But the thing that you need to know about this function in Excel is that it's only returning the p-value associated with your test. It is not telling you the actual calculated test statistic. And we know from learning what we have to report in our summaries of different statistical analyses that we always have to report that calculated test statistic. So even though this may seem like a shortcut, well, it is a shortcut, but it's only giving you one piece of information, that p-value, the probability associated with that test. But when we're reporting the shorthand for this, we have to include more than just the p-value, right? We also have to include what that obtained value was for that test statistic. So we've covered doing it by hand on a piece of paper, right? Doing it with an Excel function, and now let's talk about doing it with JMP, the easiest and probably most detailed way of running a t-test and getting output for that test. The first thing I want you all to notice, though, is that to run this independent t-test in JMP, all of the data has to be stacked. So in other words, every single row is its own observation. So that means I had to take all of my unremediated observations and I had to put them in the same column as my remediated observations. So this is sort of unlike how we usually set up spreadsheets. So just know that if you were importing a spreadsheet, you'd have to make sure these data were stacked so that all of the actual measured values are in the exact same column in JMP. Also check to make sure that you have your continuous response variable and that the grouping variable, in other words, which identifies which group each observation belongs to, that has to be a categorical variable. That's going to tell JMP to do a t-test, the fact that you have this continuous response and this categorical treatment factor, which only has 2 different levels in it. You now can head into the Fit Y by X tool from the Analyze menu. That's going to open up a new window where it asks for your Y response. So we would enter that continuous response variable, and it asks for that factor grouping, right? So which is the variable that tells JMP which group each of those observations belong to. Once you enter these 2 things in, JMP knows which sort of family of the statistical tree it should take you to. So now if you just click OK, it brings you to this visual output. Remember, JMP is very visual and it's always going to try to give you a graphic, not just spit out numbers like a p-value. And so what you're seeing plotted here are the values for all of our observations in each of these groups. And the mean is denoted, for all of them, is denoted by this gray line. So to get to the actual t-test statistics, we know we can head to the magic red triangle as always. And notice from this drop-down list, we have an option to select the t-test. Once we click on that, it tacks on this new output at the bottom, which gives us all the information we could ever possibly want about a t-test. So it's telling us, first of all, the order that it did that numerator, because that's actually one of the problems if you're using some software packages. Remember, the formula for a t-test was to take one group mean and subtract from it the other group mean. But how do you know which group was the first and which was the second? That information is necessary for you to know whether you're doing a left-tailed or a right-tailed test, because you have to know whether or not you're hypothesizing that that test statistic should be a positive number or a negative number. So right off the bat, JMP is telling you which group it subtracted from the other. It's also telling you which type of test that it runs. Note, by default, JMP thinks that we're really not that smart. It doesn't trust us. So it automatically defaults to a slightly different formula that allows us to not have to meet the assumption for equal variance. So it's telling us that right now. So that's one reason why, if you were to do this by hand and then redo it in JMP, you would find that this calculated test statistic, sorry, that's right over here, this calculated test statistic might be slightly different, because JMP is defaulting to a slightly different formula that allows you to not have to meet the assumption of equal variance. It also gives us just the straight difference between the two groups. It gives us the standard error of that difference. So how confident are we that the difference really is 40.3? What are the 95% confidence intervals for that difference? And this just tells you the confidence level it used, 0.95, in calculating these confidence levels. And then we get into the actual output from the formula. Here is your obtained value right here. They're calling it a t ratio. That is your calculated test statistic. Here's how many degrees of freedom went into determining the p-value for your test. Now again, note, it's this really funky decimal number. That's where this assumption of unequal variance comes in. They're really altering the degrees of freedom to account for the fact that you may not have equal variance. And then here's your standard output, the two-tailed probability, the right-tailed probability, and the left-tailed probability. So again, it's easy if you're doing a two-tailed test. You know to go for the one that has the absolute value markers on either side of the t. But which right-tailed test, whether it's right-tailed or the left-tailed test you have to use, really depends on whether or not you were hypothesizing that you would have a negative test statistic based on this order for the numerator, or a positive test statistic. If you were hypothesizing a negative test statistic, then you want the left-tailed test. If you were hypothesizing a positive test statistic based on this order, then you would want the right-tailed test. Okay, so all of this information packed into one little box. So we just, in like miraculous time, went over 3 different ways to do an independent t-test. But no matter which of those 3 approaches you use, you're always going to have to report the shorthand of your results in the same way. We're using this t to denote that we've done a t-test. We're putting the degrees of freedom that we had for this test into the brackets. Again, that gives the reader an idea of the power of your test. We're including that calculated or obtained t-test statistic. And then we're also including the p-value. So notice in this example, it just says p is greater than 0.05. So that means we probably did this one the old-fashioned way and couldn't report the exact p-value associated with this obtained value for this many degrees of freedom. So we're just saying it was greater than our threshold, therefore it's not significant. But if we're doing it in JMP or Excel, we can report the actual p-value associated with this test. But because so many of these inferential tests are so strongly influenced by the amount of power associated with the test, we have secondary metrics that we can use to figure out how meaningful that difference might be. Okay, so in other words, if you had a ton of observations, you might have a lot of power and find this hugely significant result. But ecologically, it might not be very meaningful. So there is this metric for an effect size called Cohen's effect size. And it's a pretty simple calculation that we can use to approximate, without considering power, just what is the magnitude of the difference between these two samples. And it's very simple. It's the same numerator as our t-test statistic, but the difference is that all we're dividing by is the mean standard deviation for all of that data. And you know that you have a pretty small effect, meaning it's not that meaningful, if your Cohen's effect size is between, say, a 0 and a 0.2. You might have some sort of a moderate or a medium level of meaningfulness if that calculated effect size is between about 0.2 and 0.5. Once you get over that 0.5 range, now you know that you're getting into something that not only is likely statistically significant, but also likely meaningful. And then the real test of all this too is whether or not ecologically it makes sense. So Cohen's effect size is something else you should always be calculating as an add-on to any significant result you get, but also know that this should make sense ecologically. So again, we just blew through the 3 different ways to conduct these tests, and we mentioned that we had to meet the assumptions for normality and equal variance. We would have had to go back and test for normality for all of those, right? We still need to make sure we're meeting that assumption. And luckily, we don't really have to go through too much hand-wringing if we find that we don't have normal data. And that's because there are very simple non-parametric tests that are available to substitute for that student's t-test that we just went over. And what's nice about these is there really are no assumptions about the distribution or the equal variance. They're usually pretty simple. They don't modify the base formula that much, and they happen to be really more robust. And because of that, it's really hard to abuse them. So the downside, like you hear this and you say, why don't we just always use these non-parametric tests? The downside is that they are almost always less powerful. By making these adjustments to the formula, you are more likely to make a type 2 error and miss a significant result when it is truly there. The most common non-parametric test for the student's t-test is a Wilcoxon test. It's the exact same thing, except we're running it on the ranked data, right? So we just, instead of using the actual measured values, we would rank the data, and then we would perform those calculations. So the reason why this is less powerful is because we're really losing information about the magnitude of the difference between observations. We might have one observation that's a 10, and the next highest observation is a 500. Well, if we rank this, all we know is that 10 was lower than 11, but we don't know that it was tremendously different. So that's why these become less powerful. So when you're in JUMP, you can go right back to that magic red triangle and ask for your non-parametric options. Notice JUMP has 3 common independent t-test non-parametric options for us. Wilcoxon is right there on the top. But you can also try the test doing the exact same formula, but using the medians instead of the averages for your 2 samples. And then the van der Waarden test is a little bit more complicated. But typically, you're fine just to go with Wilcoxon. So once you click on this, it's going to again tack on some new output to your analysis window. And notice that this Wilcoxon test for the independent t-test breaks it down into 2 separate windows. First, you have your 2-tailed result up here. Notice the absolute value brackets around the z. And then for the 1-tailed test, it's going to actually put your p-value down here using a different distribution. Okay, so don't be confused. This is the same test. It's just that the 2-tailed test result is going to be reported in sort of a separate row than the 1-tailed test. I'm going to just pause and end this video here and pick up with the dependent t-test in a new video. So this is sort of a forced break for everybody to stand up and do some jumping jacks and wake up before we launch into the dependent t-tests. Okay, so I will talk with you in a moment.